Section 2.2 is on inductive and deductive reasoning. We want to know the difference between them and then how we can prove things or find a disproof of those things. So, deductive reasoning is used when you are, inductive reasoning is used when you are looking for patterns. Okay? When you see a pattern happening in a specific case, you can often come up with a conjecture to write about that, about the general case. So now suddenly we're defining a word, inductive reasoning, using a word that we don't necessarily know what it is, which is conjecture. A conjecture is an unproven statement based on observations. Unproven statement based on observations. So we see a pattern based on some specific cases, and we make a statement about that observation. That's a conjecture. So anytime you say, hey, I noticed something, da 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 da, right? That's a conjecture that you're making. And you're using inductive reasoning to make that conjecture. Okay, so I've got some pictures up here. Does anyone notice anything about the animals in these pictures? They're all cats, right? And they're all licking their paws. So what's a conjecture that we could make based on these specific things that we're seeing, this pattern that we're noticing about these specific animals, these specific photos, that we could, what's a conjecture that we can make? Cats lick their paws, okay? We could make a conjecture, an unproven statement, that cats lick their paws. All cats lick their paws, okay? How, is it possible to prove it? How would you prove it? And not just a whole bunch of cats, but all cats. You'd have to observe every cat and make sure that every single one of them licked their paw at some point in time. Okay? I don't think we want to do that, right? But that's inductive reasoning, okay? It's kind of difficult to prove that, isn't it? Is it difficult to prove inductive reasoning? Yeah, okay? But it could potentially be possible if we could observe every single cat in the world, right, to decide whether they all have that tendency that they like to lick their paw, or not necessarily that they like to, but that they do lick their paws. Okay, so that's inductive reasoning. Here's another example of inductive reasoning in mathematics. We have some blocks up here. Okay, you don't have to draw all the pictures, but I want you to think to yourself, what would the fifth item in that sequence look like? And then when you're ready, we'll share. Can everyone picture it? Okay. So what's the fifth item in that sequence going to look like? What do you think? One more on each side. So we take our fourth item in our sequence, we redraw it, and hopefully you would do a better job than I, right? And the fifth item in that sequence just simply adds one to the left and one to the top. Make sense? Those are the kinds of problems that you will see in this section. Okay, nothing too hard, right? All right, here's the next example. This is a mathematical kind of conjecture that we're going to make. So make and test a conjecture about the product of a negative integer and a positive integer. So on your paper, make and test a conjecture about a negative integer and a positive integer's product. So first of all, you have to ask yourself, what does negative integer mean? Negative whole number, negative counting number. Positive integer, positive counting number, right? And then what does product mean? What do we do if we find the product? What other words do we hear when we hear the word product? When I think of product, I associate it with sum, difference, and quotient. Okay? But that's me. I'm a math teacher. When you think of product, you probably think of something you buy in the store, right? Shoes. Shoes are a product. Okay? So, of those, of when you hear sum, what does that mean? Addition. When you hear difference, what does that mean? Subtraction. When you hear quotient, what does that mean? Division. So when you hear product, what does that mean? Multiplication. Okay, so I want you to make and test a conjecture about the product, the result of a multiplication problem between a negative integer and a positive integer. What do you think, Nathan? What's going to happen if we multiply a negative integer with a positive integer? Okay, so Nathan's conjecture is that if I multiply a negative integer and a positive integer, the result will be negative. Do you agree or disagree? Agree? I hear one person who agrees. Agree or disagree? Agree. Hearing more people agreeing. When we multiply a negative integer and a positive integer, do we get a negative result? Yes, everyone agree? Okay. So you're trying to think of a time when you would multiply a negative and a positive and not get a negative, aren't you? Okay. When you can find that, that's a counterexample. Okay. Something that makes it false. But Nathan was correct. The result will be negative. How would we test it? You could multiply every single number ever known to man, right? Every single positive one by every single negative one, right? But we aren't going to ask you to do that to that extent, okay? But let's think about what's a positive number, Ariel. Let's pick your favorite positive number. 5, okay? And we want a negative number, Ben, Chris. So we got to get names down. I'm sorry, I am needing to work on that today. I told myself that. Third hour. Zach. Sorry, Zach. Pick your favorite negative number. -2. Oftentimes when we multiply, we like to not have the times sign, so we just put a parentheses around it. 5 times -2 is a -10. All right, Olivia, pick your favorite positive number. 1, okay? And then let's pick on Spencer. What's your favorite negative number? -3. 1 times a -3 is what? -3. It works. Okay? A positive times a negative always gets us a negative. Okay, next one. Make and test a conjecture about a negative number raised to an odd power, or any negative number raised to an odd power. Okay? Does anybody have a conjecture you want to offer up. Now that Nathan did the hard lifting for the first one. This is the second one. This is just another example. Okay? So second example. We want to make sure that we talk about it so that you know the kinds of problems that you'll be asked to do tonight in your homework. Okay? So does anybody have a conjecture about a negative number raised to an odd power? Okay? We have a conjecture that the result will be positive. Okay? Changed his mind. He said the result will be negative. Okay? So think about it. Do you agree? Is a negative number raised to an odd power going to have a negative result? Okay, so we have a conjecture. Do you agree or disagree? What do you think, Faith? Do you agree or disagree? Agree. Nathan agrees. Okay, how about you, Andre? Agree or disagree? Agrees. Okay. So, Andre, what's your favorite negative number? Negative 13. Okay. Now, we're going to raise that to an odd power. So, Jasmine, would you give me an odd power, please? What's an odd number? 3. Okay. Now, this is a big number. Okay, Andre gave us a really large number. But think about not the net result as far as the number is concerned, but what happens if we take a negative 13 times a negative 13? We'll get a positive number, right? We take that times a negative 13 again, what will our net result be as far as sign is concerned? Positive or negative? A negative. Okay. All right. Zach, give me another negative number. Negative 152 is his favorite number. Okay. Dayton, give me a negative power. I'm sorry, an odd power, my fault. 353. Okay. Now we're rapidly approaching numbers that we cannot even plug into our normal calculators, right? We're going to get scientific notation on some of these. But what will the result be, positive or negative? Negative. Okay. We could know because of our inductive reasoning, the patterns that we've seen. Okay? All right, so that's inductive. Counterexample. Okay? When we're looking for a counterexample, we're looking for any one instance where the conjecture fails. Yes, sir. What's that? Seahorses? Good. He's sharp. So I had a conjecture that only female animals give birth. Okay? So only female animals give birth is a conjecture. Okay? So in nature then we would have to observe animals, right? Make sure that only female animals give birth. So you start to look around. There's a kangaroo with a joey and a lion with her cub and a bear with her cubs, buffalo with its calf, whale with its calf, right? Is that what they call them? Okay. And we start to think in our minds of any animals, any male animals who actually give birth. And Giovanni said, wait a minute, I thought of a counterexample. What about a seahorse? Okay. And he's right. This conjecture is not true. Okay. Because a seahorse, the female deposits the eggs into the male's pouch. The male fertilizes them and carries them until they're born. And that allows the female seahorse to start making eggs again instead of having to care for the young. Okay? All right. Yeah, I don't want to show the video. Okay. Everybody good? Everybody understand what we're looking for? We're looking for a counterexample. Okay? All right. Can you guess which two pictures I took? No, no. I took the bear. No. I took the picture of the bear. I've been snorkeling, but never scuba diving and never with whales. The bear and the buffalo. Yeah, they do that for salt and minerals. Okay, so a student makes a conjecture about numbers. Find an counterexample to disprove the student's conjecture. So they made an example or a conjecture that all numbers that are divisible by 5 are odd. And 10 is not odd, right? Is that divisible by 5? Okay, so 10 is a counterexample. Probably too easy, right? But 10 is divisible by 5, and it is certainly not odd. Does that make sense? All right. That's what we're looking for there. Now, we want to talk about deductive reasoning. Deductive reasoning is what you were using yesterday with many of the math facts and definitions that you were working with. So deductive reasoning uses facts, definitions, accepted properties, and the laws of logic to form a logical argument. So now we're not looking at patterns so much as we're using facts and definitions to come to conclusions. And there are two laws that we use to come up with conclusions based on deductive reasoning. One of these laws is the law of detachment. The law of detachment says that if the hypothesis of a true conditional is true, the conclusion also has to be true. Bless you. So let's think about this. Jaden, put it away, turn it off, or in airplane mode, or do not disturb. I don't want to see it again. Airplane mode is one that basically lets you still use it, but it doesn't get any notifications. Doesn't use Wi-Fi. It does use Bluetooth, and so it can be used on an airplane safely without interfering with their navigation. Do not disturb is even very similar to that, only it doesn't turn your wireless off. So the nice thing about airplane mode is if it's turning your wireless signals off and it's not checking the tower and not checking the wireless 802.11g or whatever you're using, it's saving your battery because it's not having to touch. I don't want you to use it at all, but I'm guessing you're getting notifications and that's what's spurring you to want to look at your phone. Okay, so we're not doing that anymore. Okay. Okay, law of detachment. To airplane mode. Do not disturb. Should be somewhere in your settings. Also keeps people from making your phone make noise in the middle of the night while you're trying to sleep, like my sister would play Words with Friends at night. Wake me up. Okay, so law of detachment. First of all, tell me, what is a conditional statement? An if-then statement. And we like to use P, if P, then Q. P implies Q, if I write the Q correctly. Okay. So we have a true conditional statement. If you have been to the U.S. Capitol, then you have been to Washington, D.C. is a true conditional statement. Okay? Now, they say that the hypothesis is true. Okay? Which part was the hypothesis? Been to the U.S. Capitol, the P part. Okay? So we have a true conditional statement. They told us that the hypothesis is true. What can you conclude from that? Guess what? I've been on a tour of the U.S. Capitol. So what does that mean? I've traveled to D.C. Exactly. So then I can conclude that the Q part is also true. Okay? We like to use 3 dots, or at least I've seen this done, to mean therefore. You don't have to worry about that. But I have a true conditional statement. If you have toured the U.S. Capitol, you have been to Washington, D.C. And someone said, I've toured the U.S. Capitol. Okay, we can conclude from that that they have been to Washington, D.C. Make sense? All right, that's the law of detachment. Law of syllogism says if hypothesis P, then Q is true. And if hypothesis Q, then conclusion R is true. You can eliminate this whole hypothesis Q part and just say if hypothesis P, then conclusion R. This becomes a bridge between these two. So we can eliminate the middle stuff. So I told my daughter, if I get off work early, then I'll take you to the mall. And if we go to the mall, we'll look for homecoming shoes. Okay? So I can eliminate the whole middle part and just simply say, if I get off work early, then we'll go look for homecoming shoes. Does that make sense? Okay, a lot of times we like to shorten things up and not say all of this stuff is going on. Okay, we can eliminate the whole going to the mall, and if I get off work early, we'll go look for homecoming shoes. Okay, all right, so here's how it works. Here are some examples. The first one says the segments that if 2 segments have the same length, then they are congruent. Is that a true conditional statement? It wouldn't hurt to write this one down. If 2 segments have the same length, then they are congruent. So it's an if-then statement. That's a conditional statement. Is it true? If 2 segments have the same length, then they are congruent. Is that a true statement? Is that our definition of congruent? Remember way back when? Okay, so that's a true statement. Now, what does the picture tell us? Ariel. Good. AB has a length of 3.34. And CD has a length of 3.34, right? Okay. So we can conclude what? That they're congruent. We know AB is equal to CD. Those 2 lengths are equal. Therefore, we can conclude that AB, segment AB, is congruent to segment CD. Does everyone agree? Okay. That's the law of detachment. We have a if-then statement. 2 segments have the same length, then they are congruent. And we know that P is true. We have 2 segments with the same length. Therefore, we can conclude that Q is true. Okay? Not hard, right? Just we're eliminating a lot of writing by doing this. Okay. If a figure is a square, then it is a rectangle. Conditional statement, right? If then statement conditional. Does everybody agree that that one's true? If a figure is a square, then it is a rectangle. True statement, right? Okay, can you think of any squares that aren't rectangles? Okay, so this is my P. Figure is a square. P implies it's a rectangle. That's my Q. Okay, now this time what did they tell us? They give us P or Q here. Quadrilateral ABCD is a rectangle. Is that P or Q? That's Q. Okay, so they gave us a true statement. If P, then Q, but they told us Q is true. Can we conclude that P is true? What do you think? If quadrilateral ABCD is a rectangle, does that mean it has to be a square? No. Okay, so this is where it can fall apart. You have to say no conclusion here. Okay, because they told us a true statement, a true conditional statement, but they didn't tell us that the hypothesis was true. So we can't make a conclusion from it. Does that make sense? Okay, that's the pattern it's going to look like. So if it helps you to put a little P above the part about it being square, the implies symbol and then the Q above the rectangle, do that so that you can start to see which one they told us. Okay? All right. Let's see if we can use the law of syllogism here. If it is raining today, then soccer practice is canceled. Okay? What's the most important thing you want to put the P above here? Raining, if it is raining today. It isn't important, right? What's the most important thing about this? Raining. Okay, there's our P. Okay, now here's our then. So soccer practice is canceled. What's the most important word there? Canceled. Okay, so there's our Q. Okay, P implies Q. Raining means canceled. Okay, now if soccer practice is canceled, did we see that already? Which one was that? Q. Okay, then that's our implies. You can go to the mall after school. What's the most important word there? Mall. Okay. Have we seen mall anywhere else before? No. So we have to introduce a new letter, right? So P, Q, R is usually the next word, or next letter. So that's why they put R there. Okay. So we have a P implies Q and a Q implies R. Do we have a zigzag pattern here with these guys together in a diagonal? Yes. So what can we conclude from it? If it is raining today, then we can go to the mall after school. Okay, we can ignore the whole soccer practice being canceled part. That makes sense to everyone? Okay. Am I going too slowly? Or are we okay? All right. So let's see if this one follows a pattern. Okay. If a figure is a rectangle, what's the most important word in that statement? Rectangle. There's our P. Okay. Then all interior angles are right angles. Okay. What's the most important word here? Right, okay, so maybe we're going to put our Q there. So we have a P implies Q, Okay? If a figure is a square, what's the most important word here? Square. Okay, have we seen square already? Nope, so that becomes our R. Okay, then all the interior angles are right angles. What's our most important word here? Right. Okay, what letter did we use for right before? Q. Okay, does this fit our diagonal pattern? No, so we cannot make a conclusion here. Does that make sense to everyone? No conclusion. P implies Q, R implies Q, no conclusion can be made. Okay. Okay. All right. I think that is all I have today. Oops. I want to decide inductive or deductive, and I'm done. Okay. So the next one says, if the sum of the digits of a number is divisible by 3, then the number is divisible by 3. The sum of the digits of a number of 147 is 12, so 147 is divisible by 3. Okay. Is this inductive like we saw at the beginning, or is this deductive like we saw toward the end of the lesson? What do you think? We're not sure, so let's look at this next one, and we'll see if we can find the difference and the distinction between them. Each time you forget to do your math homework, your parents take away your cell phone privileges for a day. So the next time you forget to do your math homework, you'll lose your phone privileges. Okay? Inductive or deductive? Inductive, we have a pattern going on here, right? Okay? So when you see a pattern, that's inductive. So what do you think about this one? Inductive or deductive? We're using the laws of divisibility, right? So this one's deductive. We use laws or definitions, theorems, postulates. We'll use deductive, but if we look at a pattern and see something happening, it's inductive. Okay? All right. This is the assignment. And make sure you study your conditional, inverse, converse, biconditional, contrapositive, so that you've got those down. Don't lose that information. Well, not for a while, but just if you keep it fresh in your mind, you won't forget it and you'll learn it better.